All right, so let's go ahead and pick up where we left off with Taylor series, Maclaurin series. Any questions before we get back into it? Okay. All right, so we talked a lot about very general types of functions where you can essentially, through finding a sequence of derivatives, you can build these Taylor series up. So let's look at this case here. So this is a specific case that was sometimes called the binomial series. So let's build this general thing up, and then we can basically it'll give us a shortcut. We can apply it later. So I want to build a Maclaurin series for this thing here. I have 1 plus x raised to the power k. K is any real non-zero number. But if we think about the way that we build Maclaurin series, what do we need to start with? Or what information do we need to get? Okay, so let's find a derivative. What is the derivative of this thing here? Okay, are we okay with that? All right, now what do we need to do? So we got one derivative. Is that enough? Okay, so what's the next derivative going to be?
A times k minus 1 times x minus x plus 1.
Okay. Do we see a pattern emerging here if I want to get another one? K times k minus 1 times k minus 2. Okay. So we can see that we can kind of continue this indefinitely. I did not have a slide here where I wrote down the generalization of this. Let's go find it. This one's formula. So basically, this is kind of what we were building up to. So in starting with so we're taking 1 plus x, we're raising it to some power k, and basically we're building up all these terms starting from whatever the value of k is, and essentially decrementing that down from 1, or sorry, down by 1 each time. Actually, let me see if we can find one that's a little more generalized. Yeah, this is better. It'd be better if I could get a general one. Here we go. So this is essentially the kind of pattern we're following. So if you had to take 1 plus x raised to any power of n, this is going to be how this series expands. And because you're dealing with these products that are a little bit hard to capture in a sigma notation, the biggest thing I want to focus on here is the patterns that are kind of emerging. So your first term is always going to be 1. Followed by your power times whatever times this x. And then kind of like we saw in the general example there, we're kind of building these up by multiplying by these, decreasing factors. So n times n minus 1, n times n minus 1 times n minus 2. And just like in a Taylor series, we're going to divide these by n factorial. So this is one of the things that you're going to be expected to take advantage of in the homework. So I wanted to give a couple examples of it. So let's go ahead and do this one here. So basically our goal now is to essentially make this look like 1 plus some variable raised to a power of n. So right now, do we have that? Can we make this fit that form? Or do we have to do some manipulations? Any rewrites we could do. But
Does it need to be 1 plus n?
it does. Yeah, the first term needs to be a 1. So that's one problem we have, right? So I'll do one rewrite here. I'm going to call this 4 minus x to the power of negative 1 over 2. So we really need that first term to be a 1 instead of a 4, right? Is there any way we could make that change? So something I'll do here, I'm going to factor out a 4. So I'll factor out a 4, and then what's left on the inside here? 1 minus 1/4 x to the negative 1/2. Is it a problem that I did that, though? Is it a problem that I factored out a 4? Yeah, it still needs to be raised to the negative 1/2. So you can factor that out, but basically have to keep the power. What is 4 to the negative 1/2? So this is now 1/2 times 1 minus 1/4 x to the negative 1/2. So I have a constant 1/2. Does this part right here mimic the thing? Does this match the thing I'm trying to get to? I have first term 1. Power of n is any real number, any non-zero real number, so I'm okay. And this a is something variable. So now we can start building up a Taylor series for this. And these are going to be a little hard to generalize, so we'll write out the first few terms, then we'll kind of just leave it as something continuing infinitely. So our first term is always going to be 1. Our second term is going to be n times a. And then n times n minus 1 times a squared over 2 factorial plus n times n minus 1 times n minus 2 over 3 factorial times a cubed, and so on. Go ahead.
Does the positive, the plus and minus matter like inside of the thing? Because on the equation you put on top, it's 1 plus a to the power of n.
And we don't have, and ours is negative, right?
Yeah.
So let's do this.
Does that matter?
It does matter, but it's also, as long as you pay attention to it, it's going to be okay. So let's do this. This 1 plus a to the n is something very general. We're trying to do something very specific. So let's identify what Rn is and what Ra is. For our example, what is n? -1/2. What's our a? -1/4 x. So as long as you identify those things, we're okay. But yeah, it's just kind of like when you're doing a geometric series. Or yeah, we're trying to set up or trying to represent a function as a geometric series. It's always first term divided by 1 minus r, right? It's okay if your r, if it's 1 plus something, you just have to know to account for that. So same kind of thing here. So our series is gonna, let's just kind of start populating this. First term is 1. And that's always a consequence of, if as long as we're in this form here, our first term is gonna be 1. One thing I totally forgot is that we're multiplying all this by 1/2, right? All right, what's the second term going to be? Essentially, what's n times a in our case? 1/8 x. And then how about the next one? We should write this one out, right? So -1/2 times -3/2 times what's a squared? 1/16 x squared all over 2 factorial. So before we simplify that, any question about how that got, about where all those terms came from? Okay. Should we do one more, or now let's go ahead and stop there. I'm going to run out of room. But I know this thing goes indefinitely. So now let's clean some stuff up. We have 1/2 times 1 plus 1/8 x. What does all this stuff come out to be? It's positive, right? Positive. What is 8 times 16? 108? I think that's the next term, but somebody check me. So it's 2 times 2 is 4, but we're divided by 2 as well, right?
Oh, you're okay.
Yeah. So I'm trying to do the whole thing at once.
Yeah, 128. 8 times 16.
80 times 128. Thank you. So 3 over 128 x squared. Are we okay with that? Okay. So last move here equals 1/2 plus a 16th x plus 3 over 256 x squared, and so on. So questions on how we got the first few terms. All right. Go ahead.
That 1/2, you just brought it down from the equation on top, right? So you have to multiply all the terms.
Yeah, so reminder there, this binomial series thing only really works for things that fit this form. So one of the first things we had to do was to basically deal with the fact that that 4 was in that first position. How we doing? Okay. So one thing we haven't talked about is radius of convergence. That is going to come directly from A. So I want my absolute value of A to be less than 1. And this is not the thing where you have to Like typically when we have this radius of convergence, we have to check the endpoints. This is not one of those times. We can say that the radius is strictly less than 1. Anything greater than or equal to 1 will give us divergence. So if this is generally true, what is our A for this example? So negative 1/4 x. I want that to be less than 1, right? So from there, what can I say about x? Eventually, I would like to say something about the absolute value of x itself. So can I keep essentially, how can I isolate the absolute value of x? Multiply by 4. So one thing I'll point out here is this. The absolute value of negative 1/4 x is equal to this. The absolute value of negative 1/4 times the absolute value of x. What is the absolute value of negative 1/4? 1/4. So I get 1/4 times the absolute value of x is less than 1, which means the absolute value of x is less than 4. So as long as x is between negative 4 and 4, we have convergence, we have divergence everywhere else. So once you kind of get the hang of using this binomial series setup, it'll be a good shortcut. Before you get used to it, it'll take some getting used to, but there are a few things on the web work and the written homework and probably on the next test that deal with this. It'll probably save you some time. So any questions on this? Okay. So this is an example we've kind of been talking about for a while, this strange function and how we can use it, or basically how we can turn this into a polynomial. So I want to find a Maclaurin series for it now that we have all the tools to do so, and see how good of an approximation that is, for what values of x it converges for. So what information do we need?
Derivatives.
We need derivatives. So what is the first derivative of this natural log? You remember how to find derivatives of this thing? It's a little bit complicated.
You split it up to natural log of 1 plus x minus natural log of 1 minus x.
Let's see. So you're saying this is true. The natural log of 1 plus x over the natural log, or over 1 minus x, is equal to this. The natural log of 1 plus x minus the natural log of 1 minus x.
Yeah.
Is that true? It is true. I don't know if I'd want to deal with the derivative directly. I think this is a much better way to go about it. So now I can treat this function as this. So now can I deal with those derivatives one at a time? What's the derivative of natural log of 1 plus x? 1 over 1 plus x. How about the natural log of 1 minus x? So negative 1 over 1 minus x. I think that makes them both positive. So 1 over 1 plus x plus 1 over 1 minus x, right? Okay. So this is what the derivative looks like. It's the sum of these two terms. If I'm trying to build a Maclaurin series, which is a specific type of power series, is there anything I can rely on with the way this derivative looks? I have 1 over 1 plus x and 1 over 1 minus x. I think these are actually, at least one of these is exactly something we've done before.
Yeah, one of them is just. Are you talking about the Maclaurin or the powers?
That's the point. That's part of my point here. Is there not? So everything we've done before Taylor series, Maclaurin series, like Taylor series allow us to take any function you want and turn it into a power series by finding a bunch of derivatives, right? All the stuff we did with like before that was all based on geometric series. Those things are going to be equal if I can, like if I can make it look like a geometric series, it'll be equal to the Maclaurin series. These power series representations are they're unique. So it's kind of like, here's a weird example. If I want to find the derivative of 5x squared, what is that? 10x. What would the derivative be if you found it using the quotient rule? You might have a hard time imagining how you would even set that up, right? But it would still come out to 10x, right? So here's the thing, their derivatives are unique. If a function has a derivative, I don't care how you take it. If you do it correctly, you're going to wind up in the same place. Power series representations of functions are unique. I don't care how you do it. If there are 5 ways to do it and you do them all correctly, they're all going to take you to the same place. So I could find a bunch of derivatives. I could find the derivative of 1 plus x, then find the derivative of that, then find the derivative of that, and see how they generalize. But I think in this rewrite that Colin had us do, this opened up some shortcuts that we've kind of been taking advantage of.
You can use power series for.
Yeah. I don't think this first one would be that. Okay, first of all, do we agree that 1 over 1 plus x and 1 over 1 minus x, those look like geometric sums, like sums of geometric series? What's the common ratio in 1 over 1 plus x? It's not x. It's negative x. Because the sum of a geometric series looks like this. First term over 1 minus r. Which kind of reminds me of what I was talking about with Isabel is if you have like the wrong sign there, a sign mismatch, that's okay. You just have to know how to work around it. So I think this first one here is 1 minus x plus x squared minus x cubed plus minus so on. How about this bottom one? All positive terms, right? Okay, so what the heck did we build? And how does it relate to the thing I actually wanted to do? And if I add them together, what are they?
What is the odd terms canceling?
They would. So let's see how this works. So first term is going to be 2, right?
Oh.
Then what? Is that all it is? It continues, right? But it should just be, yeah, all the coefficients are going to be 2 because essentially all the even powered terms are going to get doubled and all the odd powered terms are going to cancel out. We believe that? Okay. But what is this? Is this thing right here f of x? We'd have to integrate it, right? Because this right here really is, this is f prime of x. Remember, this whole thing was built on the derivative of natural log of 1 plus x over 1 minus x. So what I really want to do is find f of x. All right, so what's that going to be?
Let's keep it. Yes, 5.
Okay, can we generalize this thing? So each term goes up by a power of, they count up by powers of 2, right? So I should have something that looks like this, x to the 2n. Is that complete? Minus 1? Plus 1. I had n equals 1 down there, but really we should start at 0. So is that going to make the powers match up correctly? Yep.
Yeah, the same on the bottom. And then we should have 14.
Okay, does that cover everything? So that is going to be, even though it doesn't look like a polynomial, it is a polynomial for, it's an infinitely long polynomial for natural log of 1 plus x over 1 minus x. So are we okay with how we build that? One more thing I want to point out is this. We made this thing for the derivative. Is this thing here a geometric series? What is the first term? 2. What's the common ratio? So could I say that this is a good representation of that? What happens if you integrate 2 times x to the 2n? It should be the thing that I've already boxed in, right? So another reminder, you can kind of choose to integrate or take a derivative of, depending on which direction you're going, either after you generalize or before you generalize. You're going to wind up in the same place if everything goes correctly. How are we doing? Do we know what the radius of convergence should be? We could do the ratio test, but there's another way to get there that I want to make sure we remember. We built this from geometric series, right? So based on these geometric series, could we say the radius of convergence is absolute value of x is less than 1? Is that fair to say? If I integrate that, what happens to the radius of convergence? It stays the same. So my radius of convergence should be the absolute value of x is less than 1. Because that is something that gets preserved when you take a derivative or you take an integral. If you knew the radius of convergence before you did any calculus on it, that's going to remain the same. So yeah, we found a polynomial for natural log of 1 plus x over 1 minus x. Doesn't converge for very many x values, but that representation still exists. Questions? Okay. So one last thing I want to show you from this chapter. Because we have a lot of these things available to us now, we can talk about limits that look like this. So any suspicions about what we think this thing does?
Goes to 0.
How do you know it goes to 0? Or when would you think that? So I got one person saying it goes to 0, one person saying that e to the x is going to grow faster than the rest of the things in that expression. So those kind of seem at odds. Let's do a couple things here. I want to rewrite this. So I'm going to rewrite it as I'll just split up all the terms. E to the x over x squared minus 1 over x squared minus x over x squared. Do we have suspicions about any of these individual terms now? Like, do I know what 1 over x squared will do? Do I know what x over x squared might do? What do we think these are going to do? The second and third terms go to 0. Any idea about the first one here?
Goes to infinity.
Goes to infinity. Okay, so let's make sure we're right. One thing that I want to point out here is this. One of the very first things we did was this series. I think we said e to the x is equal to, and I'm going from memory, so maybe I shouldn't. This is equal to 1 plus x plus 1/2 x squared plus 1. So yeah, if anyone wants to look at a couple days ago in their notes, I believe that e to the x is equal to this series. Okay, so x to the n over n factorial. So this is another way I can use to look at this. So I'm going to transform this limit one more time. What is e to the x over x squared? Can't I just decrease all these powers by 2? So 1 over x squared plus x over x squared plus 1/2 x squared over x squared, so plus 1/2, and then plus 1/6 x, and so on, right? So all I'm really doing there is dropping in, basically I'm re-representing e to the x over x squared as this new thing. I'm going to drop in the other terms that we know about, minus 1 over x. So first of all, is it clear why I'm allowed to do that? So one thing I want to point out is when I say e to the x is equal to this, I'm not using the approximately equal signs. I'm not using the word approximate. E to the x is equal to that sum. Exactly. So because of that, I can substitute one in for the other. Do I know what's going to happen to all these terms as x gets very large? So a lot of these are going to go to 0, right? But then what's going to happen to 1/2? Well, that's just 1/2. What's going to happen to 1/6 times x? That's going to go to infinity. So this limit also goes to infinity. Are there other ways we could look at this limit? Does L'Hopital's rule apply here? It should, right? What does the numerator do? Goes to infinity. What's the denominator do? Right. So I could also look at the limit of the derivatives. So that's e to the x minus 1 over 2x, right? I can use L'Hopital's rule again, right? What does that limit do? Goes to infinity, right? So another way to get there. But basically, yeah, now feel free to use these Taylor series to build polynomials and have them stand in for basically any function whose derivatives you can find. Go ahead.
You did the beginning, right? And then at the end you put minus 1/x² minus
Yeah.
1/x. It's from the top.
Yeah, so these two terms,
And how do you know which one out of those three to get the limit from?
I got the limit from all of them.
Oh, so
Yeah,
the
you-
limit of 1/x² is 1/x².
Sorry, what was say that again? I lost you in the middle there.
So the limit of minus 1/x² is minus 1/x².
Well, that would be. No, I'm not saying the limit is. All I did was just rewrite that term. But when you can start evaluating that limit. In fact, I could have done it before I wrote that down, because I know that for 1/x², if I have a constant denominator and the numerator is growing, that's going to trend to 0. Same with x/x². I didn't take the limit yet, so I kept writing those terms down.
Okay.
What else?
But yes, basically,
Okay.
it would be the same thing to get the limit of the 3 and then subtract them.
Yeah, we can add them all together. In general, that only really works if all the limits exist, which in this case they don't, right? Because yeah, a lot of these things go to 0, which ends up becoming irrelevant because there's going to be a bunch of terms in here that have positive powers of x that are going to go to infinity. Good question. What else? All right, that is all we have for this chapter. So, I don't think it's anytime soon, but we don't have a ton of class between now and then. I think the next test happens on the 20th. But really, how many class periods are between now and then? I don't see you Friday, right? So Monday is the 13th. So 13, 15, 17. So we have basically 3 more periods. So the next test is going to cover all of what chapter was this? 8. And the first 2 sections of chapter 9. So that's where we're going now. So I would love to have most of that Friday, the 17th, be like a review day. But yeah, 9-2 is where we have to get through. So we only got a few minutes. Let's kind of set the stage for the kind of things we're going to be talking now. So getting into parametric equations, polar coordinates. We're going to start with parametric equations and talk about what exactly that means. This graph right here, is this a function? Why is it not a function? What's that? I have x's overlap. What do you mean by x's overlap? So there are some x values, and we can just pick one, right? Here's an x value. The way we think about functions is, what is f of x? Well, that needs to be exactly one thing, right? In this equation, this curve, that is clearly not the case, right? So let me ask this question. We're saying no because we have x's overlap. I haven't heard anybody say it yet, but I would bet money that many of you are thinking of the vertical line test. But what is the vertical line test really like? Why does it exist? Right, and that's essentially what it's doing, is making sure that for every x you have a unique y. So let's back up a little further. What is a function? In mathematics, what is a function? You've sort of already said it, but let's be really explicit. Right, so basically a function is, and yeah, for the way Munia said it, for each x value, there's a distinct y value. lots of ways to define it. I'll say this. So you have domain and range, right? Domain's a bunch of input values, range is a bunch of output values. We usually call those things X and Y, but really they don't have to be, you can call them whatever you want. But for if I have a function, then for everything in the domain, the function maps a single thing in the domain to a single thing in the range, right? So you've probably seen the bubbles before. Here's my domain, here's my range. If I have a function really and truly, then every single one thing in here better go to one thing over here, right? Is this legal? Is that still a function, or did I violate something? That's a function, right? Let me do something else though. Is this legal? No, that's a problem. So I can have multiple inputs go to the same output. That's okay. That's still a function. I cannot have a single input go to multiple outputs, right? Okay. So, but that's, I think we've kind of been going off the assumption that the domain is where the x's live and the range is where the y's live, right? But really a function, as long as you talk about the domain and range in a careful way, we can talk about this weird curve being a function. So let's look at it this way. Now, instead of x and y being the domain, let's throw the bubbles back in. I'm going to say that my domain values are these values of t. So if I have a t value in here, it gets mapped to a range or something in the range. And what do those things in the range look like? They look like points, xy points. So I'm not asking you to give up on your definition of function because it's correct and it is the definition of what a function is. But basically, for the kinds of things we're going to look at now, we're redesignating what the inputs and outputs look like. I'm not taking an x value, letting the function act on it and mapping it to a y value. I'm taking a t value, like the value of a parameter. So when I mentioned these are called parametric curves, that's essentially what the t is. The t is kind of the input parameter that governs what xy point you're looking at. So these things, if we look at them through this lens, these are functions. If I take a t value, then they map to a single point. That still works for what we call functions, right? Okay, so let's try to at least start looking at an example before we break. So I'm going to graph this curve, and I'm going to graph it on, the same axes we usually do, x-axis, y-axis. So even though I'm telling you this thing is a function, its graph is not going to look like the things that you typically call functions. So let's make a table. My input is t, my output are these xy pairs, and I'm going to try to use those to figure out what this curve looks like. So when t is equal to -2, what are the x and y going to be that correspond to it? Is it 8? And how about the y value? -1. Let's get all these really quickly. When t equals -1, I should get, these are easy to fill in. -1 squared is 1, plus 2 is 3. 8, 3, 0, -1, 0. Are we okay with all that? But if I graph that, what's that going to look like? So let's say this is 8. First point is 8, -1. So what am I graphing?
X and the Y.
X and the Y, right? So even though the T is the input that drives all these things, it doesn't show up in the graph. Basically what the T does is it helps us kind of order these points and how to connect them, but I'm not really graphing them. So my second point will be here. Third point will be 0, 1. -1, 2. And x equals 0, y equals 3. So what this curve is going to look like is, so even though all those points have nothing to do with t, the t is going to tell me how they form a curve. I need to connect those in order. So I think if I were to have asked you this 2 minutes ago, is this curve a function? You probably would have unanimously said no. But building up the way we did, there is a way for us to look at this as a function, as long as we define our inputs and outputs more carefully. So any questions, kind of like this new paradigm I'm bringing up. Okay, so we'll get into that more on Monday. I'll be upstairs in a few minutes. Otherwise, enjoy your weekend and I'll see you Monday.